Tactical superiority on the modern battlefield is rarely the result of abstract military doctrine. It is the direct application of physics and engineering. As militaries operate across the overlapping domains of land, sea, and air, they move into the fourth generation of warfare. In this environment, a platform's survival relies on how effectively it integrates with the rest of the operational network. An effective modern warfare system requires three specific characteristics: interoperability between different units, redundancy to absorb localized losses, and scalability to project force across vast distances. But these operational goals are bound by the physical limits of kinematics, thermodynamics, and electromagnetics. To understand survivability in multi-domain operations, we have to look past armor plating and weapons payloads. We have to mathematically deconstruct the limiting equations governing platforms in each domain. In coordinated ground operations, tracked combat vehicles act as the primary nodes of force projection. They are required to hold territory, absorb kinetic strikes, and return ballistic energy. Providing cover requires heavy artillery. Traditional towed systems create a static footprint, while self-propelled guns integrate artillery directly onto a mobile chassis. The advantage of the mobile chassis becomes obvious when evaluating the kinematics of modern ballistics, using the advanced towed artillery gun system as a baseline. This diagram plots the parabolic trajectory of a 40-kilogram shell, fired at 800 meters per second, elevated at 45 degrees. Gravity at 9.81 meters per second squared sets the time of flight, maximum vertical height, and final horizontal impact range. The moment a weapon fires, radar tracks the incoming shell. By running the parabolic equation in reverse, the enemy computes the precise origin of the strike and launches counter-battery fire. The firing platform is now trapped within a vulnerability window dictated by the shell's time of flight. A self-propelled system like the K9 Vajra T addresses this vulnerability through a shoot-and-scoot strategy. It fires its payload and immediately relocates before the counterstrike arrives. To escape, an 80-ton platform must overcome inertia. An internal engine outputting 2,000 horsepower converts chemical energy into 1,490 kilowatts of mechanical power. Applying 150 kilonewtons of tractive force, we calculate the seconds required to accelerate to 50 kilometers per hour. If acceleration takes longer than the enemy's counter-battery time of flight, the platform is hit. Survivability relies directly on a platform's power-to-weight ratio. Out on the open water, the variables change. Fleets deploy a spectrum of operational vessels, from heavy destroyers to agile corvettes. In the maritime domain, survival is dependent on early detection. A ship's situational awareness is governed by the electromagnetic limitations of its radar system. This interface shows a corvette's radar array. Spinning at 15 RPM, it requires 4 seconds for a full 360-degree scan. The tight 1.6-degree beam mathematically restricts dwell time, meaning at 500 pulses per second, only a fraction reflect back from a target. We can apply these sensor limits to an active threat scenario, an incoming torpedo targeting a naval destroyer. This map charts intercept mathematics. A torpedo is launched at 40 knots from 6 kilometers away, while the destroyer evades at 30 knots. Converting to meters per second, we calculate if the destroyer can escape the blast radius before the torpedo closes the gap. This underlying mathematics perfectly explains the strategic role and necessity of modern submarines. Submarine platforms utilize nuclear or diesel-electric propulsion, each balancing endurance, operational depth, and acoustic noise signatures to avoid triggering a ship's localized sensors. By utilizing stealth, a submarine shrinks the enemy's effective radar detection range. Reducing the initial detection distance from 6 kilometers to 2 kilometers drastically reduces the time available for the target to execute evasive action. Joint operations extend these mathematical constraints into the airspace, relying on high-performance indigenous platforms like the Tejas Mark 1A. Consider a tactical scenario where a fighter jet detects a surface-to-air threat and must execute a rapid altitude change to escape the missile's engagement envelope. This graph charts the ascent. A fighter cruising at 800 kilometers per hour climbs 2,000 meters at a vertical rate of 220 meters per minute. Factoring time required and horizontal speed reveals the ground distance covered. Every evasive action reduces operational range. Because gravity imposes weight limits, aircraft fuel capacity is capped. This makes logistical support platforms, like mid-air refueling tankers, mandatory to sustain operations. If a fighter burns 2,400 kilograms of fuel per hour at cruise and a tanker transfers fuel at 1,000 kilograms per minute, it takes a 4-minute window to secure a 4,000 kilogram payload mid-flight. Whether utilizing manned flights or advanced manned-unmanned teaming, aerial combat superiority remains tied to these fuel-to-weight ratios and consumption rates. True interoperability requires bringing all of these equations together. A successful joint operation synchronizes artillery trajectories, radar sweep timing, and fighter jet fuel logistics into a single strike. An integrated battlefield management system computes these overlapping domains in real time, aiming to improve the operational efficiency of every deployed asset. The shift into fourth-generation warfare introduces unmanned underwater vehicles and autonomous aerial drones that are engineered to exploit the physical and mathematical limits of manned platforms. Unmanned systems operate without human life support constraints. This permits high-risk mission profiles and aggressive scaling that would be impossible for manned vessels. When networked together, high-density drone swarms bypass traditional air defense layers by directly attacking the sensor limitations we calculated earlier. A high-density drone swarm overwhelms the fractional dwell time and pulse repetition limits of shipboard radar. By injecting thousands of simultaneous returns, the swarm exhausts the receiver's processing capacity, creating mathematical blind spots. Simultaneously, the deployment of directed energy weapons, or DEWs, bypasses traditional kinetic constraints. Firing a concentrated beam of electromagnetic energy changes the baseline rules of artillery kinematics. Because a laser moves at the speed of light, the time-of-flight equation drops to 0. There is no parabolic arc, no gravity variable to calculate, and no window of time for a tracked vehicle to execute a shoot-and-scoot escape. Kinematics and thermodynamics built the foundation of modern military strategy, but the introduction of non-kinetic and autonomous systems shifts the cost per engagement, defining a new set of physical constraints for the next generation of warfare.